Okay, we have here today another interesting integral from the MIT Integration Meet 2012. This one was problem 22. We have the integral of x cosh x over sinh x squared dx. Okay, my first thought on this one, I noticed that we have this cosh and sinh over here on the right, and this works well together. So this integral, what I have here in blue, this would be pretty easy. This would be a very straightforward integral. Only trouble is we have an x here. And the thing with the x, it doesn't really work well with our trig functions, right? But now we're in a situation where we have something that's pretty easy to integrate. We have something we can differentiate. I think what we want to do is use integration by parts on this. And what I'm going to do is I'm going to use the DI method, or tabular integration. This is just kind of a shorthand for integration by parts. And what I'm going to do is I'm going to differentiate my x because we know that's going to be easy to differentiate, and when we differentiate it, it's going to reduce. So this is going to be pretty nice over here. And then I'm going to integrate all this other stuff. Like I said, this here isn't going to be too hard to integrate. So we'll integrate this chunk. And then with our table, we're going to have alternating signs. So this next row is going to be a minus. We'll differentiate x. I'll get 1. We'll integrate this thing, but I think I'm going to go and take this and integrate this over here to the left. So let's just make this a separate integral with what we have here. Now, the reason I say this is going to be pretty straightforward is because we can do a u substitution on this, just noticing that the derivative of sinh is cosh. So if I do a u substitution, I'm just going to call my u equal to sinh x, take my derivative, our du value is going to be just this whole numerator, which is cosh x dx. Okay, that's a mess. So we'll just go ahead and we'll make the substitution. So I'm going to have du in the numerator, and this is going to become u squared. And I actually could write this as, we could put it back in the numerator and write it as u to the minus 2. So integrating this is going to give me minus u to the minus 1, or this is going to be just minus 1 over u, but our u is sinh x, and so this is actually going to become minus cosecant, hyperbolic cosecant x. So let's just take this and we'll put it back into the table. Okay, now from here in our DI method, the diagonals are going to be part of our solution. So I'm just going to write this part down. We're going to have minus x hyperbolic cosecant x. And then this row here, this is actually going to be an integral, but we have minus times minus. So that's going to give me a plus. So we just need to find the integral of hyperbolic cosecant of x. But now this is a pretty common integral, so we could just do this with a formula, but I think I'm going to do it out just because I don't think I've done an integral with a hyperbolic function in a while. So to integrate this, what I'm going to do is I'm going to put it back into the form of 1 over sinh of x, like this, because that's the same thing as hyperbolic cosecant. And then what I'm going to do is multiply numerator and denominator by sinh, like this. So we're just multiplying by 1. Now what's going to happen here, we're going to have sinh in the numerator, then multiplying in the denominator, this is going to give me sinh squared x. But then let's just look at our identity that we can use for sinh squared of x. So the nice thing about the hyperbolic trig functions is we have a lot of the same identities, just with a slight variation. So this is kind of like our sine squared plus cosine squared equals 1. Instead, we have cosh squared minus sinh squared equals 1. Just rearranging that, we get a value for sinh squared. So what I'm going to do is take this and put this back in my denominator here. So when I rewrite this, what I'm going to have in the denominator is we're just going to put down cosh squared x minus 1 dx. And now, again, I'm in good shape for a u substitution where my u is going to be just cosh. So we'll make that our u. I'll take my derivative. Again, the derivative of cosh is just sinh. So we're going to write this. We're going to write sinh x dx. And let's see if I can squeeze a little more in here. So in our numerator, we're going to have just du, and this is going to become u squared minus 1. So for this, let's just do this out really quick with partial fractions. So I'm just going to do it over here in the space that I have. But we can write this, we could factor this as u plus 1, u minus 1, and then we would just want to solve, well, I'm really not giving myself much space here. Let's see if I can do it though. So we can have this fraction and we can break it up like this, and we just need to solve for our a and b values. And what we can do is use the cover-up method on this. So like what I can do right here, for u minus 1, I plug a 1 in here, cover that up, plug a 1 in here, and then evaluate this fraction. So that's going to give us 1 over 1 plus 1, or 1/2. So our b value is going to be just 1/2. Hopefully you can excuse the mess, but what I'm going to do, again, the same thing here. We're going to plug a minus 1 in here, but that would give 0. We don't want to divide by 0, so we cover it up, and then we plug in the minus 1 here. That's going to give me a minus 2 here, 1 over minus 2. That's going to give me my a value, which is minus 1/2. So what I'll do is take this and put it back into the integral like this. So we're going to have our a value minus 1/2 over u plus 1. And then we're going to break this into a second integral with our b value 1/2 over u minus 1. And at this point, I'm out of space for real, so I need to do something. Okay, so now we can go ahead and integrate. So we're just going to have here minus 1/2. This is just going to become natural log absolute value u plus 1. And then again, we're going to have 1/2 here. We could basically pull it up front, but I'm just going to do it all together. It's just going to give me natural log absolute value u minus 1. Well, I can factor a 1/2 out of this. And then with the property of logarithms, I can combine these as a fraction and write it as u minus 1 over u plus 1. But what I'm going to do, actually, I want to simplify this before I back substitute. I'm going to remove the absolute value just for a moment. What I'm going to do is multiply by the conjugate here, top and bottom. So I'm going to multiply by u minus 1, u minus 1. This is going to give me, when we multiply this out, we're going to have u minus 1 squared here. We still have a 1/2 out front. This here is going to become u squared minus 1 when we just distribute this out. But now again, we can take this 1/2 power by the property of logarithms and bring it into the exponent. So it's going to cancel this square here, and then we can just put a square root on the denominator. So I know that's kind of messy, but let's just rewrite this. And what I'm going to do is back substitute now. We have our u equals cosh of x. So what's going to happen here in the numerator, we're going to have cosh x minus 1. Then here, this is going to be in the denominator. We're going to square root cosh squared x minus 1. Okay, now here what I can do is take a look at this thing and notice we can go back to our identities over here on the right and notice this is the same thing as sinh squared x. So we can rewrite this as sinh squared x, but it's inside the square root. So when I take the square root of that, that's just going to give me over here in the denominator, it's just going to become sinh x. And technically we could leave it this way, but what I'm going to do is divide the sinh into the numerator so that we have this. We can write this as natural log of hyperbolic cotangent of x minus 1 divided by sinh is going to be, again, just like our cosecant, it's going to be our hyperbolic cosecant of x. And yes, again, we could have done this with a formula because our value for this integral is going to be this right here. So I'm going to just take this and plug this back in. So our final solution is going to be, we need this piece. So for our final solution, we're going to have just minus x hyperbolic cosecant x. And then this thing, natural log hyperbolic cotangent minus hyperbolic cosecant x. Put a plus c on there, and that's it. Okay, good problem there today, so we'll stop it there. Thanks everyone for watching. Have a great day.